All right, chemists, welcome to another lecture in our lecture series here for AP Chemistry. This is chapter 14, the properties and structures of acids. Let's go ahead and get started. All right, so during our last couple of conversations, we've had a look at some calculations involving acids and bases in solution. Today's conversation is going to focus less on the quantitative aspects of acid-base chemistry and more on an understanding about how we can relate the structure of an acid to its behavior within a solution. In order to have a thorough understanding of an acid structure, we first off need to have an understanding about which type of acid specifically we are dealing with. Many of these acids we have seen before, but I just want to make some clarifications here between the different types of acids you're likely to encounter on the AP Chemistry test. Starting with the first of these, which is what we refer to as a binary acid. Binary, again, a term meaning two. So a binary acid is always going to be made up of hydrogen bonded to a nonmetal. And the classic binary acid, which you're all familiar with, is hydrochloric acid. For the nomenclature involving binary acids, as a bit of a review from last year, recall for binary acids, we give them the prefix hydro, and then the stem of the nonmetal's name, and then the suffix ic acid. So again, for HCl, it would be hydrochloric acid. For H2S, it would be hydrosulfuric acid. So whereas a binary acid is made up of two atoms, hydrogen plus a nonmetal, that is in contrast to a ternary acid, otherwise known as an oxoacid. These oxoacids are made up of hydrogen plus a nonmetal plus some number of oxygens. And a number of these familiar acids would count as oxoacids that you've seen already in this class. Those would be things like sulfuric acid, nitric acid, perchloric acid. Brief review again of the nomenclature of these oxoacids. The ternary acids, recall, are based around the name of their parent acid. You should have committed to memory those parent acid names from previously having seen them on a number of occasions. And to name the acids in the family of a parent acid, we change the prefixes and suffixes according to the number of oxygens which are bonded to the nonmetal. If there's one extra oxygen in comparison to the parent, we give it the prefix per and the suffix ic acid. If there's one fewer oxygen than the parent acid of the family, we change the suffix from ic to us. And if there are two fewer oxygens, in addition to changing the suffix from ic to us, we're also going to add the prefix hypo onto the parent acid's name. And so a common example from this would be the chloric acid family. The parent acid, chloric acid, has the formula HClO3. With one extra oxygen, we would have HClO4, that is perchloric acid. One fewer oxygen would be HClO2, that is chlorous acid. And then two fewer oxygens in that family, we would have HClO, otherwise known as hypochlorous acid. So both binary acids and oxoacids, those ternary acids, are familiar to you from your nomenclature from last year. Another group of acids which you've seen a little bit in this particular year here is organic acids. Organic acids are defined by the presence of the carboxyl functional group in the organic molecule. The most common of these organic acids that you're going to come across in the AP chemistry test is a familiar acid, which is acetic acid, otherwise known as ethanoic acid. All of these, again, contain the functional group that you discussed back in chapter 22, which is the carboxyl group, which is the carbon double bonded to one oxygen, and then we have the single bond to the second oxygen with the hydrogen, the acidic hydrogen, off of that single oxygen right there. And then last but not least here, a type of acid that you've seen on a number of occasions before, but maybe didn't necessarily know that it had a specific name associated with it, is what we refer to as a polyprotic acid. Poly being a prefix meaning multiple or many, and protic referring to a proton which is able to be lost, that is, a hydrogen ion that can be lost to another species. So again, a polyprotic acid is essentially an acid which has multiple hydrogens that can be lost in Bronsted-Lowry acid-base interactions. For each of those hydrogens to be lost, there would be a specific Ka related to the loss of that particular hydrogen. So for example, for the familiar polyprotic acid sulfuric acid, the loss of the first proton is essentially going to go 100% in solution because the first dissociation of a hydrogen from sulfuric acid is a strong dissociation. But the loss of the second hydrogen there is going to have a much smaller Ka than the loss of the first, because at this point, we're now essentially attempting to remove a hydrogen from an already negatively charged species, which is going to, again, be a less favorable process from a thermodynamic standpoint, and therefore we'll have an equilibrium that lies further to the left, meaning each subsequent dissociation or loss of a proton is going to be an event that more heavily favors the reactant side than the previous. So those are, again, the types of acids. We'll examine some of these in greater detail over the next couple of slides. All right, so the first of the types of acids we're going to look at in greater detail here today is going to be specifically the polyprotic acids. One kind of classic polyprotic acid the AP test will sometimes ask you about is a familiar species here, H3PO4, otherwise known as phosphoric acid. And if you have a look at the dissociation equations, which we've written along the left-hand side here, you'll note here that we can describe that dissociation of phosphoric acid in a sequence of steps, each time showing the loss of a single proton from the molecule. So initially, starting with the molecular acid H3PO4, upon dissociation, we yield one hydrogen ion and the anion here, the conjugate base H2PO4 1 negative. And recognizing again that phosphoric acid molecule has multiple hydrogen ions which can be lost, we could then write a second dissociation equation showing the loss of one of those other hydrogens off of the H2PO4 1 negative ion. Continuing that process along, losing those hydrogens one by one. So down at the bottom there, we've given you the overall equation for this dissociation process, in which the H3PO4 ends up losing 3 H positive ions, leaving us behind with the phosphate ion PO4 3 negative as the other product of that reaction. But again, because each of these dissociations is a weak dissociation, that implies that each of the first three reactions written here is a reaction which fairly heavily favors the left side of those equations. And so for each one of those dissociations, we could write an individual K describing the dissociation equilibrium for that step. So let's go ahead here and write the K expressions for each of the stepwise dissociations, and then we'll compare that to the overall K for the complete dissociation of the phosphoric acid molecule. Starting off with the first of those dissociations, our equilibrium constant, Ka1, we'll label that, is going to be equal to products over reactants, that would be the concentration of the hydrogen ion, H positive, times the dihydrogen phosphate ion, H2PO4 1 negative, divided by the concentration of our reactant there, that is the molecular acid H3PO4. And you'll note here, I've already provided you with the values of these Kas for each individual step along this dissociation sequence. The Ka for the first step there, you'll note, is 7.5 times 10 to the negative third, a very small Ka value, implying again that phosphoric acid is a relatively weak acid. Now for the second dissociation step here, we'll go ahead and again write the Ka expression. This time it's going to be products over reactants, concentration of H positive times HPO4 2 negative, divided by the concentration of our reactant, that is H2PO4 1 negative. And note this time here, our Ka for the second dissociation step there is now 6.2 times 10 to the negative 8th, significantly smaller than even the dissociation of the first proton, which again was also itself a weak dissociation. So what you'll see here now is that the dissociation of each subsequent step is getting smaller, implying again that it is less favorable to remove a proton from a species which is increasingly negatively charged as more and more and more of these protons drop off. For the third of our dissociations here, we'll go ahead and write one more Ka expression. This time products over reactants is concentration of H positive times concentration of PO4 3 negative, now all divided by the concentration of HPO4 2 negative. And again, following the same trend we've observed here, now our Ka for the third dissociation is incredibly weak, that is a Ka value of 4.8 times 10 to the negative 13th. So again, each subsequent loss of a new proton is less favorable than the one that came before it. That is to say, each of the anions formed from the dissociation is a weaker acid than the one which came before it in the dissociation sequence. Now, something I'd like you to note here is for the overall reaction, that is the dissociation of the species H3PO4, we could write an overall K for that expression, which would be equal to the concentration of hydrogen ion, now raised to the third power, again because we're losing all 3 protons in the overall reaction, times the concentration of the polyatomic phosphate PO4 negative, divided by the molecular acid concentration H3PO4. And as it turns out, we have a way that we can actually derive the Ka from the overall dissociation here by looking at the Kas of the individual steps along the way. Something I'd like you to note here is what happens when we multiply the Ka values of each individual step from the first 3 stepwise dissociations. Taking Ka1 times Ka2 times Ka3 gives me again H positive times H2PO4 1 negative over H3PO4 times the Ka2 of H positive times HPO4 2 negative divided by H2PO4 1 negative times the Ka3 there, which is now H positive times PO4 3 negative's concentration divided by HPO4 2 negative. And you'll notice here, as I multiply each of those K values by one another here, that the intermediate ion species are going to end up canceling out in both the numerator and the denominator. That is, we see here in Ka1, we have the dihydrogen phosphate in the numerator, and that dihydrogen phosphate ion also shows up in the denominator of Ka2, so we can cancel those out. You'll also see that we've got the hydrogen phosphate ion, HPO4 2 negative, in the numerator of Ka2, and in the denominator of our Ka3, so we can cancel out that intermediate ion as well. And after making those cancellations, what you'll see here is left over is in our numerator, we've got 3 of those hydrogen ions showing up. That is to say, the concentration of hydrogen ion is going to be cubed. And also in our numerator, you'll see there we've got the phosphate ion, PO4 3 negative. You'll notice here the only thing which is not canceled out of our denominators is that concentration of the molecular acid H3PO4, which leaves us overall then with the concentration of hydrogen cubed times the phosphate ion over the concentration of the molecular H3PO4, which is the value of the overall Ka from our expression we just derived up above. So we can determine the Ka for the overall dissociation of the acid by simply multiplying the Kas of the individual stepwise dissociations along the way. And as we do so, you'll see here that by multiplying Ka1 times Ka2 times Ka3, we multiply these values together of 7.5 times 10 to the negative third, times 6.2 times 10 to the negative eighth, times 4.8 times 10 to the negative 13th, we get a new value here for the overall K expression of 2.2 times 10 to the negative 22nd. That is a very, very, very small equilibrium constant indeed, which should make logical sense because each of those individual steps by themselves were unfavorable. So taking together all 3 of those steps together, it seems like a system that heavily favors the reactant side, which again does make logical sense because phosphoric acid was a weak acid for its first dissociation, and each subsequent dissociation again is also increasingly weak, meaning the probability of losing all 3 of those protons from an individual phosphoric acid molecule is going to be very, very low. Again, this is a system which heavily favors the reactant side. Now, a couple things to note there again, just as we previously mentioned, the K values decrease as you go along the dissociation sequence, again attributable to the fact that we're removing protons from more and more negative species as this dissociation proceeds. And then again, the second thing to note there is that those intermediate ions formed through that dissociation sequence themselves are amphoteric species. That is, in addition to acting as proton donors in these dissociation equations we've written here, we also could see this reactions run backwards in the other direction, seeing them pick up protons from the solution, forming things with more protons attached. That is, they can act as the conjugate base in each of these weak acid interactions. So that's what we're looking at here for polyprotic acid. Let's move on to our next slide. All right, so now that we've had a look at the behavior of those polyprotic acids and their dissociation sequences, we're now going to go ahead and have a look at an example problem here to quantitatively have a look at the ideas discussed in the last slide. What example 1 is going to ask us to do here is to calculate the pH of the solution as well as the concentration of all ions present, all species present, in a 5.0 molar solution of phosphoric acid H3PO4. And before we get started with any sort of calculations whatsoever here, I think it would be a good place to start by simply listing all of the species present in the solution so that we can know what we're kind of after here in terms of our calculations. So starting off here in terms of major species, obviously we're going to have water present in our system. And then again, we've got the phosphoric acid there, which is going to be the major species, because as we noted from before, phosphoric acid is a weak acid, and therefore the equilibria are going to heavily favor the left-hand side there, which means we're going to have a lot of H3PO4 in our solution as well. In terms of other species present, from the dissociations equations of the phosphoric acid molecules, we're going to see definitely the loss of hydrogen ions as the acid exhibits its acidic behavior, donating those protons. And we'll also see the conjugate base anions, which are formed through those dissociations. That is, the phosphoric acid will dissociate first to form the dihydrogen phosphate H2PO4 1 negative ion, the hydrogen phosphate HPO4 2 negative ion, as well as the phosphate ion that is PO4 3 negative. And then again, because this is an aqueous solution, in addition to all those other ions, we're also going to have the one other one you got to watch out for there, which is the hydroxide ion present as well. So now I've got a list of all of our different acid species we're going to be going after here. The next thing we can go ahead and do here is from things we've already previously seen in the past here, we can go ahead and set up an ice table for the first ionization of that phosphoric acid molecule. So let's go ahead and write out our equation. That is H3PO4 is going to dissociate, producing an H positive ion, and the dihydrogen phosphate H2PO4 1 negative as well. And we're going to go ahead and ice this thing here, plugging in the information with which we've been provided for the initial concentration of 5.0 molar for the H3PO4. And again, we're going to assume zeros for both the hydrogen ion and for the anion H2PO4 1 negative. We can again define our change in concentration as we have previously as a minus X for the molecular acid, and we'll see a plus X moles per liter for both the hydrogen ion and for the dihydrogen phosphate anion, leaving us with equilibrium concentrations of 5.0 minus X for the molecular acid, and then X and X for the two anions on the product side of that reaction. So again, we've set up our ice table here, and we can also, as we've always done before, write our Ka expression. The Ka for this dissociation, we're going to go ahead and label this one as Ka1, because again, this is the first of the dissociations here. For Ka1, we're going to see the Ka value equal to concentration of H2PO4 1 negative times H positive. Those are the two products, divided by our molecular acid H3PO4 on the denominator of our K expression there. And as we have previously, we'll go ahead and solve our ice table here by making an assumption. From having a look at our previous page, we saw that the Ka1 value for the first dissociation of phosphoric acid was 7.5 times 10 to the negative third. And that Ka is now going to be equal to our concentration of the two products of the first dissociation. That is going to be an X for both the hydrogen ion and the dihydrogen phosphate ion, so X squared in the numerator, divided by 5 minus X in our denominator. And again, we're going to go ahead and make our assumption here. In making the assumption, our equation simplifies down to X squared divided by 5 when we assume that X is a very small change in concentration with respect to the initial molarity of 5 molar of the phosphoric acid. And at this point here, we can now go ahead and solve the equation here for X. We're going to go ahead and multiply both sides by 5. We are going to take the square root of both sides, and we'll go ahead and get an X value here of 0.19 molar. Now, having calculated our X value, if we look back to our ice table, we recognize that that X value now gives us the concentration both of the hydrogen ion produced from that first dissociation of the phosphoric acid, as well as the dihydrogen phosphate ion H2PO4 1 negative. And at this point, we can also make a quick calculation of the concentration of the molecular acid H3PO4 at our equilibrium position. Real quick, looking at our sig figs, if we start off with an initial concentration of 5.0 molar, and we subtract from that value the 0.19 molar X value at equilibrium, this is going to give us, therefore, 4.81, which would then round with our sig figs to 4.8 molar for the phosphoric acid molecular species in solution. So, our first ice table is taken care of right here, and we've found the concentration of several of the species within our solution. Now, the trick to moving forward from here is to have a look at what we know about the relative values of Ka2 and Ka3 for the dissociation, the second and third dissociations of the phosphoric acid molecule. In comparison to Ka1, Ka2 is a value of 6.2 times 10 to the negative 8th, and Ka3 is a very, very small K value. That Ka3 is 4.2 times 10 to the negative 13th. Implying, therefore, the second and third dissociations are significantly less favorable than that first dissociation of the phosphoric acid molecule. And as such, the degree to which those dissociations occur is going to be orders of magnitude smaller than that first dissociation. Implying, essentially, even though each of those subsequent dissociations does produce hydrogen ions in solution, the amount of hydrogen ion produced by each of those subsequent dissociations will be orders of magnitude smaller than the amount of hydrogen ion produced from the first dissociation of the phosphoric acid. And as such, we can safely ignore the contributions of hydrogen ion to the solution from those subsequent dissociations. And you'll see now that this actually makes my life much easier going forward to calculate the concentrations of the remaining ions. So I'm going to go ahead now and record my calculated X value of 0.19 molar as the concentration of hydrogen ion in my solution for that first ice table. And I can then use that concentration of hydrogen ion going forward in calculations for the remaining ion concentrations rather than using an ice table, instead by simply manipulating the K expressions for Ka2 and Ka3 for those subsequent dissociations. We'll see how we do that as follows. Let's go ahead now and write out a K expression for the second dissociation here, the Ka2. That second dissociation, recall, occurs when the dihydrogen phosphate ion, H2PO4 1 negative, splits apart to form an H positive ion and HPO4 2 negative, implying, therefore, the constant here, the equilibrium constant Ka2 for that dissociation would be the concentration of H positive times the concentration of HPO4 2 negative divided by the concentration of H2PO4 1 negative. And having written now that Ka expression, I'm going to go ahead and rearrange that expression to solve for the concentration of the ion HPO4 2 negative. So rearranging the Ka expression here, I get concentration of HPO4 2 negative is equal to the Ka2 value multiplied by H2PO4 1 negative's concentration, and then divided by the concentration of hydrogen ion H positive. And have a look now about what I actually know about for this equation now. First off, I have a value of Ka2, which for our expression was 6.2 times 10 to the negative 8th. And as it turns out, I also actually know the concentration of those other two ions, that is H2PO4 1 negative and the hydrogen ion H1 positive. As we just discussed, that hydrogen ion concentration, which we found to be 0.19 molar, isn't going to appreciably change due to the second dissociation. And so I can go ahead and assume that that concentration will be equal to the equilibrium concentration after the second dissociation as well. So I'm going to plug in that value of 0.19 molar into hydrogen ion's concentration spot there. And also the ion H2PO4 1 negative, I also can use the same value there of 0.19 molar for that concentration, again recognizing that I solved for that value out of the previous ice table, and recognizing that that species there, H2PO4 1 negative, is itself a very, very weak acid given the very small value of the Ka there of 6.2 times 10 to the negative eighth. Because that Ka is so small, that implies, therefore, that the dissociation will be very, very, very heavily favoring the left side of the equation there, and therefore the initial concentration of H2PO4 1 negative is likely not going to appreciably change as the second dissociation occurs. So in essence, what I'm doing here is assuming that the equilibrium concentration of that species will be essentially equivalent to its initial concentration, at least to the degree which I can accurately measure within the sig figs we have given in this problem. So this now makes the calculation of the concentration of HPO4 2 negative an easy solve here. Taking Ka2 of 6.2 times 10 to the negative eighth, multiplying by 0.19 molar, and then dividing by the hydrogen ion concentration of 0.19 molar. This gives me, therefore, a concentration of HPO4 2 negative of 6.2 times 10 to the negative eighth molar. And having now calculated that value, there's only one more ion from the dissociation sequence I now need to find. That is the concentration of the phosphate ion PO4 3 negative. And we're going to follow a similar logical stepping pathway here to solve for that one. This time I'm going to go ahead and write my expression for the Ka expression of the third dissociation of this triprotic acid. So for the third dissociation, we've got hydrogen ion concentration multiplied by the phosphate ions concentration divided by the hydrogen phosphate ions concentration, HPO4 2 negative. And yet again, we're going to go ahead and rearrange that equation to solve for the phosphate ions concentration. Concentration of PO4 3 negative would therefore be equal to the Ka3 value times the concentration of HPO4 2 negative divided by the concentration of hydrogen ion H positive. So at that point, we're going to go ahead and plug in some values, applying the same logic we applied before. The Ka3 value now for this dissociation was 4.2 times 10 to the negative 13th. I'm going to then multiply that by our value here of 6.2 times 10 to the negative 8th molar. That is, again, the concentration of HPO4 2 negative we previously calculated from our last expression. And again, I can use that concentration as my equilibrium concentration by recognizing again that because the K value for the dissociation of the species is so small, the concentration is not going to appreciably change from the initial conditions into the equilibrium conditions. And then we can all divide that by the concentration of H positive in solution, which again would be 0.19 molar. And I can plug in some numbers there again, and this time I get a calculated concentration of the phosphate ion PO4 3 negative of 1.3 times 10 to the negative 19th molar. That is a very small concentration indeed. All right, and at this point, we've now calculated the concentration of all of those ions formed from the dissociation sequence of phosphoric acid. The only ion remaining in solution we have not yet calculated is the one that's present in every aqueous solution, that is the hydroxide ion OH negative. And this is easy cleanup here from this point on. We can find the concentration of hydroxide by manipulating our Kw expression. That is the value of Kw 1.0 times 10 to the negative 14th is equal to the product of the concentration of hydrogen ion H positive times hydroxide ion OH negative. So I'll just do a real quick rearrangement of that equation to solve for hydroxide's concentration. That gives me Kw over concentration of H positive. And plugging in some numbers there, 1.0 times 10 to the negative 14th divided by 0.19 molar, that is the concentration of hydrogen ion. That should yield my hydroxide concentration, which I calculate here to be a value of 5.3 times 10 to the negative 14th molar. So there we have it. You've seen here how we can now calculate the concentrations of all ions present in an aqueous solution formed from the dissociation of a polyprotic acid. All right, so the next thing we're going to have a look at here is a problem that's actually shown up in relatively recent years on free response questions for the AP test. That is making a comparison of the relative strengths of the binary acids in comparing both their polarity and the bond strength between hydrogen and the halide present in the acid. So take a look at the table which we've supplied you with here. You'll see here we've listed for you 4 binary acids containing the nonmetal in the halogen family there, starting with hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And we've listed there for you the bond strength of each of the bonds between hydrogen and the halogen which it is bonded to. And you'll notice here that the fluorine has the greatest bond strength when bonded to hydrogen, and the iodine has the weakest bond strength. And we could probably justify the relative strengths of these different bonds by taking into account the size of the atoms involved. Again, with a smaller sized fluorine atom there's going to be a tighter hold on the electrons, and therefore it's going to require more energy to pull them apart. So we see bond strength being one factor which might influence the strength of an acid. Now, the second thing we'd like to have a look at here is the relative polarities of these different species. Starting off with the most polar obviously in this instance is going to be the hydrofluoric acid molecule, recognizing that fluorine is the element with the greatest electronegativity of any element on the periodic table at 3.98 Pauling units in comparison to hydrogen's electronegativity of 2.2. So we've essentially got a difference of 1.78 Pauling units between those two, leading to a highly polar bond between those two elements in that molecule. Now, in comparison here, the weakest electronegativity of all of the atoms in the halogen family listed here is iodine, whose electronegativity is only 2.66 Pauling units, meaning the hydrogen-iodine bond is the least polar bond among the 4 species present right here. And having a look here overall then, in terms of the trend for polarity again, the trend for polarity is essentially going to follow the trend for electronegativity. So the HF is the most polar bond, the HI is the least polar, and we descend accordingly. Now, that being said, making a comparison here about the strengths of the acids, recall from our discussions in previous points of this course that the 3 binary acids, hydrochloric, hydrobromic, and hydroiodic acid, are all strong acids, whereas hydrofluoric acid here is weak. Now, we might expect that the hydrogen atom is going to be more partially positive in the hydrofluoric acid molecule, making it a better target for being pulled off by another element and in some sort of Bronsted-Lowry interaction. However, it appears that the polarity alone cannot really describe to us here why the acids are behaving the way they do. And we would have to instead justify our observations based upon the bond strength. So even though the hydrogen is the most partially positive in the hydrofluoric acid molecule, because the bond is so much stronger in hydrofluoric acid than it is in any of the other binary halide acids here, hydrofluoric acid actually ends up being weak in comparison. And the trend will actually continue as it turns out. Although hydrochloric, hydrobromic, and hydroiodic acids are all considered strong acids overall, of those 3 acids, hydroiodic is actually considered to be the strongest of those acids and among the strongest acids that exist in an aqueous solution that you might normally encounter. So it appears here that bond strength really is, to a greater degree, the defining factor here about the acid strength rather than polarity. Now, if we take a look at example number 2, however, we might need to reconsider our understanding here. In example number 2, it tells us the bond strength of a carbon to hydrogen bond is 413 kilojoules per mole, which puts it at a little weaker bond than the bond between hydrogen and chlorine in hydrochloric acid. The question then asks, why is it that methane, chemical formula CH4, does not exhibit acidic properties within an aqueous solution? And to justify that, we really have to take a look at the other factor in our data table there. Even though it appears that the carbon to hydrogen bond would be an easier bond to break apart than the hydrogen to chlorine bond, methane doesn't really exhibit any appreciable acidic behavior, and that must be because the hydrogen itself is not a good target to be lost in a Bronsted-Lowry acid-base interaction from a methane molecule. We can justify that understanding by looking at the difference in electronegativities between carbon and hydrogen. So again, whereas hydrogen has an electronegativity of 2.2 Pauling units, Carbon's electronegativity is 2.55 Pauling units, meaning the carbon to hydrogen bond is an almost nonpolar bond. And as such, the hydrogen does not end up partially positive from the interaction between those two atoms within the molecule. Because the hydrogen atom is not partially positive, it's not going to be attractive to water molecules within an aqueous solution. And as such, we won't have a tendency for that hydrogen ion to leave the carbon and join a water molecule to form a hydronium. So even though the methane molecule contains a weaker carbon to hydrogen bond than hydrochloric acid does, we still don't see methane exhibiting any appreciable acidic behavior due to the nonpolar nature of the carbon to hydrogen bond, not leaving the hydrogen partially positive and therefore a target for interaction with a polar water molecule. So now that we've had a look at the polyprotic acids and the binary acids in terms of their acidic behaviors and structure, the last one we'd like to talk about with this lecture is the relative strength of an acid within the ternary acid family. In particular, we're going to have a look here at 4 acids, all of which fall within the family of chloric acid, that is HClO3. Listed here, we've got perchloric, chloric, chlorous, and hypochlorous acid. And we've kind of diagrammed for you here a skeletal structure of each of these acids. Again, not a complete Lewis dot structure, but just the skeletal structure, as well as the respective Kas of each of these acids for their dissociations. As it turns out, looking at those Kas, you'll notice here that the relative strength within a family of these ternary acids increases along with the increasing number of oxygens which are present in each species. That is to say, the strongest acid in this family is perchloric acid, HClO4, and the weakest acid within this family is hypochlorous acid, HClO. And you can see here that we're orders of magnitude difference in terms of the relative Ka values between these species. We can justify our observation here that increasing the number of oxygens within a ternary acid tends to increase the strength of the acid by understanding that oxygen itself, again, is an incredibly electronegative element. That is the second most electronegative element on the entire periodic table after only fluorine. Because oxygen is so electronegative, it's again going to be fantastically good at drawing electron density towards itself. So if you consider the position of the acidic hydrogen here, the more electronegative oxygens are present on one side of the molecule, the more of the electron density in the oxygen to hydrogen bond is going to be drawn away from that oxygen to hydrogen bond, in effect weakening that bond and simultaneously making the hydrogen more partially positive and therefore a more attractive target to another water molecule to come along and pick that hydrogen off. In addition, we recognize that when we lose the hydrogen, we're going to end up forming a negatively charged anion. With a greater number of electronegative elements right there, we're essentially going to see a more stable conjugate base anion with more oxygens present in the molecule to essentially spread that negative charge out around. So again, long story short here is the more electron density you draw away from the oxygen to hydrogen bond, the weaker the bond becomes, and the more partially positive the hydrogen becomes, making it a more attractive target to be lost to another water molecule in a Bronsted-Lowry interaction. And in addition, we stabilize the conjugate base anion with more electronegative oxygens present within the structure to distribute the negative charge in the anion around. So, I hope from our conversation here today, you've now seen that we can make some connections and correlations between molecular structures and behavior. And really that's kind of the big key idea we want to take away here, is that even though we haven't really talked about things into quantitative of a sense here, we can still qualitatively predict acidic behaviors based upon an understanding of molecular structure. So that's it for this lecture. Thanks so much for listening. We'll see you on the next one.